Hi everyone. So I want to prove our first real theorem about the pebble game, which is that if you have a graph that gets accepted by the pebble game, it is guaranteed to be 2-3 sparse. All right, so what do I need to show to do this? Well, 2-3 sparsity means that if I take a subset of vertices where I'm going to let n prime equal the cardinality of this subset of vertices, and I need to assume that I have at least two vertices in my set. Okay, so what we need to show is that if E prime is the set of edges on the subgraph of G induced by the vertices in V prime, then the number of edges in that induced subgraph is less than 2n prime minus 3. So the way we'll do this is we'll use that corollary that we did in the last video at the end. So the corollary said that if I look at the number of pebbles on the vertices of this set V prime plus the number of edges that start in V prime and point out to vertices outside of V prime, plus the number of edges that start and end in V prime, so that's the edges in E prime, then that is equal to 2n prime, okay? So the way we're going to use this corollary is I'm going to show you now that this number is always greater than or equal to 3. So if I subtract that from both sides, I get that the number of edges in E prime is less than or equal to 2n prime minus 3. All right, so let's do that. So we'll show now that the number of pebbles on V prime plus the number of edges pointing out of V prime is always at least 3. So it's at least 3 at every stage of the pebble game, all right? Well, certainly it's true at the initialization of my game board, so initialization. Why? Well, when I initialize my game board, I put 2 pebbles on every vertex, and there are no edges. So the out degree of V prime is 0, and since V prime has at least 2 vertices in it, there'll be at least 4 pebbles. So the number of pebbles is at least 4, all right, which is greater than or equal to 3. So what I need to show is that if I assume at some state of the pebble game, I'm going to assume that I have, at some state of the pebble game, I have this inequality satisfied, then if I do any pebble game move, either pebble search or edge insertion, I'll still have that afterwards. Okay, so there are two things to consider. Let's first consider what happens when I pebble search. Okay, so what happens when I pebble search? Well, the pebbles move around, right? But let's think about this. If a pebble comes in to V prime from outside, when it comes in on an edge, that edge gets turned around. So the number of pebbles in V prime goes up and the out degree goes down. If a pebble gets sent out as the pebbles are moving around, it goes out on an out edge, and then that out edge gets turned around, right? So the net change of pebbles V prime plus out degree V prime is always going to be 0. So I'm going to say during pebble search, a pebble leaves or enters, maybe that's the more natural one to talk about. A pebble enters v prime, and then I must have gone out to get it, so that edge turns around. So this is pebbles plus 1, and the out degree will be -1. So those cancel out, and the pebbles v prime plus out degree v prime stays the same. Similarly, a pebble leaves v prime. It would leave on an out edge that gets turned if it, let me see, if a pebble goes like this, it was here, and it goes like that, then the pebble leaves, and if a pebble leaves a vertex, oh, a pebble only leaves a vertex if you came in, that's what happens. So if a pebble leaves a vertex, so here's my little vertex with a pebble on it, how does it leave a vertex? Well, I had to have come in on an in edge looking for it, and so it goes out and gets reversed like this. So if it leaves the vertex, that vertex gains an out degree. So you can see again, it's always a wash on a pebble search. All right, so what happens on an edge insertion? Well, there are a few different cases to think about. Basically, I need to think about when I have an edge that I insert, there are two vertices, and those vertices can both be in V prime, or one of them can be in V prime, or neither of them can be in V prime. So let's see what happens in case 1, where I have my set V prime, and both U and V are in the set. Well, if I do an edge insertion, it means that there must have been, before the edge insertion, there were 2 vertices on U and 2 vertices on V, and I knew I had this pebbles V prime plus out degree V prime greater than or equal to 3, okay? So that was satisfied before. And then what happens after? Well, again, here's my V prime. Afterwards, U only has 1 pebble on it, V still has 2, and U has an out edge. So before, I must have had pebbles V prime at least 4 in order for me to insert this edge. And now what happens? Well, I only subtract 1 pebble when it goes in. So I still have at least 3 pebbles, which means pebbles of V prime plus out degree of V prime has to be at least 3. Okay, so what happens in case 2, where case 2, let's say, here's V prime, U is sitting inside it, V is out here, and I have to have 2 things here and 2 things here before in order to insert the edge. And then what happens after? Well, here's V prime, U has 1 pebble, an out edge pointing to V, which still has its pebbles. So nothing changes at V. So this is no change to number of pebbles or out degree or anything like that. We don't have to worry about that. We really have to worry about only what's happening to the vertices that are in V prime. And so what's the change here? The only change is that pebbles U goes down by 1, and the out degree of U goes up by 1. So the net change is equal to 0. So this means that if I had pebbles V prime plus out degree v prime greater than or equal to 3 before, it's going to be the same after, because I have decreased the number of pebbles in v prime by 1, because I stole 1 from you, but I've increased the out degree of u by 1 because the edge that I inserted points out of u to this little v that's not in the set v prime. Okay, so what are my other cases? Well, I could be inserting an edge between vertices u and v where neither of them is in v prime. Well, that doesn't then affect the number of pebbles on v prime or out degree of v prime at all. Or I could be inserting an edge from u to v where u is outside and v is inside. But in that case, if it's pointing from u to v in, the out degree and the of v prime and the number of pebbles on v prime don't change at all. So there are 2 other cases. 2 other cases. One is that u is not in v prime and v is in v prime. And the other case is that both u and v are not in v prime. And in both of these cases, edge insertion just doesn't affect. So it just doesn't affect the number of pebbles sitting in v prime or the out degree of any vertex in v prime, right? Because in both cases, the important thing is that the u, the only place where the number of pebbles or the out degree changes, is not in v prime, right? So if I knew I had at least, if I knew that the pebbles on v prime plus the out degree of v prime was at least 3 before the edge insertion, it's going to be the same afterwards. So therefore, in all cases, therefore, it must be that if I had pebbles v prime plus out degree v prime greater than or equal to 3 before either a pebble search or an edge insertion, it will also be true after that pebble search and edge insertion. So it always holds, which means that then if you go back and look at the corollary, the number of edges in E prime is less than 2n prime minus 3. And we're done.